Somehow I feel like we
okay. Maybe we can start now. Okay. It's a pleasure to welcome Gustavo Jasso to the seminar. This is the 70th meeting of New Directions in Group Theory and Triangulated Categories. And today's speaker is Gustavo Jasso from Lund, and he'll be talking to us about non-uniqueness of strong enhancements.
Yeah, thank you, Radip, for the introduction and also for the invitation. Yeah, it's amazing that it's already the 70th meeting of the seminar. So I'm really happy to be here. Yes, so as it was already mentioned, I will talk about certain results on uniqueness and non-uniqueness of so-called strong DG enhancements, sometimes also called strong uniqueness of DG enhancements. In fact, more often called strong uniqueness of DG enhancements. And before I forget, let me mention that all of this is joint work with Fernando Muro. You can find the paper already in the archive. It's our only paper together. It's called the Derived Auslander-Iyama Correspondence, in case you're interested in this. So let me begin by providing some motivation. And for this, I will remind you of a very famous theorem of Bernard Keller from 1994. So what does the theorem say, or the part of the theorem I'm interested in for today is the following. Let T be an essentially small, idempotent complete, algebraic triangulated category. Algebraic meaning that it arises as the stable category of a Frobenius exact category. Then what Bernard Keller proved is that the existence of a generator of this triangulated category T as an idempotent complete triangulated category, namely an object with the property that the smallest idempotent complete triangulated subcategory of T containing that object is T itself, also called the thick subcategory generated by G. The existence of such an object is equivalent to the existence of a DG algebra A, such that the compact derived category of A is equivalent as a triangulated category to the given triangulated category T. Yeah, so the compact derived category of A is also called the perfect derived category in the literature, and is the full subcategory of the unbounded derived category of A spanned by the compact objects, the compact DG modules. So looking at this theorem, we see that many triangulated categories that one is interested in practice in representation theory or algebraic geometry or symplectic geometry are controlled by DG algebras. So there is a very natural question that arises by looking at this theorem is, if we fix T and G, when can we guarantee that the DG algebra A is unique up to quasi-isomorphism of DG algebras? So more precisely, if I have two DG algebras whose cohomologies, which are of course graded algebras, are identified with the graded endomorphism algebra of the generator G that is fixed in the also fixed triangulated category T, what condition can I ask in order to deduce that A and B are quasi-isomorphic? And why is this interesting? Well, quasi-isomorphic DG algebras have equivalent derived categories, but not only that, their derived categories are equivalent, or so more precisely quasi-equivalent as DG categories. This means that the DG algebras A and B share all sorts of interesting properties and invariants. Okay, so now before continuing, just a quick disclaimer. Throughout, everything I will say would assume that we work over a perfect field K, for example, a field of characteristic 0 or an algebraically closed field. This is because we need a good behavior of bimodules over certain finite dimensional algebras. Yeah? So there's some technical condition for our results. So let me now continue. So I will now try to make the previous question more precise by introducing the notion of a DG enhancement following Bondal and Kapranov. For this, I first need to introduce the notion of a pure triangulated DG category. So just a very brief reminder, a DG category is nothing but a category enriched in cochain complexes of K vector spaces where K is our ground field. So that is, it's a category in which for every two objects, I have a chain complex of morphisms between them, and the composition satisfies the graded Leibniz rule, that is given by a morphism of chain complexes between the appropriate tensor product of chain complexes on one side and the output chain complex on the other side. Okay. So Bondar and Kapranov in 1990 introduced the notion of a pre-triangulated DG category. We will say that an essentially small DG category A is Karoubian pre-triangulated if the DG Yoneda embedding, which is given to us simply by the theory of enriched categories that sends an object in the DG category A to the representable DG bimodule represented by that object A, indicated here on the right. Well, this functor induces, after passing to zeroth cohomology, an equivalence between the zeroth cohomology of A and the compact derived category of A. So here I just make the point that the compact derived category of A has a natural structure of, the natural structure of a DG category. And as one can do with chain complexes, one can take the zeroth cohomology of a DG category by taking zeroth cohomology at the level of each chain complex of maps to obtain an ordinary category. And this is at the level of which we are making this statement. And every DG functor induces a functor between the corresponding cohomology categories. Yeah, so, and here Karoubian is makes it implicit for us that the zeroth cohomology of A is idempotent complete. So one does not need to require this condition, but for us it's convenient to include it in the definition of a pre-triangulated DG category. Via this equivalence, we see that if A is a pre-triangulated DG category, then its zero cohomology is canonically a triangulated category with the triangulation inherited from the standard triangulation on the compact derived category of the essentially small DG category A. So with this notion, we are now able to introduce the notion of an enhancement, more precisely a DG enhancement of a triangulated category, due also to Bondal and Kapranov. So we will say that essentially small DG category A is a DG enhancement of a triangulated category with suspension functor sigma and triangulation delta if A is a pre-triangulated DG category and there exists an equivalence of triangulated categories between the zeroth cohomology of A and our triangulated category T, where the zeroth cohomology of A is endowed with the transferred triangulation from the compact derived category of A. Yeah. I emphasize that, I mean, there is a little bit of variation in the literature, whether one says that a DG enhancement includes the data of not just the category A, but the datum of the additional equivalence of triangulated categories. Here, for simplicity, I will just consider A to be the enhancement, and I will just ask for the existence of this equivalence of triangulated categories. And this is because of the equivalence relation that I will consider on enhancements, as we will see soon, does not really make reference to any precise or any specific equivalence of triangulated categories of this form. Yeah. So as I just said, I'm interested not just in DG enhancements of T, but in DG enhancements up to a certain notion of equivalence. So we will say that two DG enhancements A and B of the same triangulated category T are equivalent if they can be connected by a zigzag of quasi-equivalences of DG categories. Yeah. In particular, notice that a quasi-equivalence of DG categories will induce an equivalence between the corresponding triangulated categories, each of which is equivalent to T in some way. However, I'm not asking for any compatibility between the quasi-equivalence here and some equivalence of triangulated categories that witness the fact that A and B are enhancements of T. So this is the reason why I did not include the datum of this equivalence in the datum of an enhancement. So we will denote by differential graded enhancements of the triangulated category T with suspension functor sigma and triangulation delta by this symbol. The 3 comes from triangulated, later we will extend this notion a little bit to something called D+ triangulated categories, in case you're wondering why this subindex. And this is the set that we are interested in describing. Moreover, we will say that this triangulated category T admits a unique DG enhancement if this set of equivalence classes of DG enhancements of T contains a single element, consists of a single element. And yeah, just to emphasize that in the literature, normally one includes the equivalence of triangulated categories phi as part of the datum of an enhancement, but then one drops it when defining the notion of equivalence between DG enhancements. So at the end, the set that we are describing is the same set that is considered always in the literature. So now we want to know when is this set a single element. So let me tell you some results that are known about this. So the following k-linear triangulated categories are known to admit a unique DG enhancement. So starting already from work of Bernard Keller that applies, for example, to the derived category of a ring, and going later through work, so seminal work of Lunds and Orlov in 2010, then further progress by Kanonako and Stellari, Niemann Stellari also most recently in 2022, more or less, in some sense, completed the program that proves that all derived and homotopy categories of abelian categories admit a unique DG enhancement. Yeah, many of these results don't need k-linearity, but just is because yeah, I was fixing this k-linearity since the beginning, and they also prove this for certain algebra-geometric derived categories that are of interest. Also, in the same work with Fernando Muro, in general, yeah, I will explain more about this later. But first, work by Fernando alone in some case, and then together in more general cases, namely in the case when we have a triangulated category that is algebraic, home finite, and Krug-Schmidt, so that every object decomposes as a finite direct sum of indecomposables with local endomorphism ring, and that moreover admits a so-called D-set cluster tilting object, also admits a unique DG enhancements. I will say more about this later. So there are, to my knowledge, there are not many more general results about uniqueness of DG enhancements. There are maybe so for some special DG algebras or some, intrinsic formality type results. So results about when a DG algebra is quasi-isomorphic to its cohomology, for example, as a DG algebra. So it, in some senses, yeah, there. Yes, I said I don't know that many general results of this kind. A big class of categories is obtained as derived categories of abelian categories, right? So this is maybe one big class of triangulated categories that are known already to admit that unique DG enhancement. So there are also negative results about uniqueness of DG enhancement. So there are some categories that do not admit a unique DG enhancement. These were constructed first by Rizzardo and Van den Berg in a series of papers where they constructed first, well, examples that admit a non-unique DG enhancements, and also k-linear triangulated categories that do not have any DG enhancements at all. Yeah, so that can also happen. So one can have a triangulated category without any DG enhancements at all, or with several inequivalent DG enhancements, so representing different points in that previous set of equivalence classes of DG enhancements. In the Z-linear case, so not necessarily working over a field, based on an example of Schlichting, Duggar and Shipley constructed algebraic triangulated categories that are Z-linear, that have non-unique DG enhancements. So they're algebraic, so they have enhancements, but they are not unique. And also a famous example by Fernando Schroeder and Strickland from 2007 constructs a Z-linear triangulated category without any enhancements at all, not DG or algebraic or topological, if you want, in terms of stable infinity categories, say, or spectral categories. Yeah. So then this can also happen. Yeah. So this is just to illustrate that the question of whether enhancements exist and whether they are unique or not is in some sense a subtle one. You can also see somehow from the time it took from establishing the uniqueness of the G enhancements for the derived categories of rings that it's implicit in Keller's work, all the way to the final result by Kanonako, Niemann, Stellari that covers all derived categories of abelian categories, that this was somehow, yeah, a difficult process. Okay, so that being said, so that's all I want to say at the moment about the G enhancements. Now I want to introduce a more refined notion, which is that of what we call a strong enhancement of a triangulated category, which in this way, as far as I know, was introduced by Lunds and Orlov in 2010. So a strong DG enhancement of a triangulated category T is now really a pair consisting of a DG category A that is pre-triangulated and an equivalence of triangulated categories phi between the zeroth cohomology of A, which is now canonically a triangulated category by virtue of A itself being pre-triangulated as a DG category, and our given triangulated category T. And now the point is that we will really use this equivalence of triangulated categories for defining an equivalence relation on all the possible strong DG enhancements of T. Yeah. So just make the same comment as before. In the literature, one would call such a pair already a DG enhancement of T. I'm reserving this word. I'm reserving the word strong DG enhancement for the pair and enhancement just for the DG category A. So now we introduce a natural variant of the equivalence relation introduced before for enhancements, which is now really making use of the strong DG enhancement. So the preferred equivalence of triangulated categories phi that witnesses the fact that A enhances T. So this is now generated by the existence of quasi-equivalences from A to B, but with the property that the induced functor of triangulated categories obtained by passing to zeroth cohomology commutes up to natural isomorphism, which is not part of the data, with the corresponding equivalences of triangulated categories phi MC that witness the fact that they are part of the data of the strong enhancements A phi and B psi. Yeah? So this is the subtle difference between the notion of a DG enhancement and the notion of a strong DG enhancement. So here we're really asking for a compatibility between the quasi-equivalences that we use to identify A and B and the equivalences of triangulated categories that we have as part of the strong enhancement. And again, we now obtain a set of strong differential graded enhancements of the triangulated category T. And this is the set that we wish to understand. And as before, now we will say that T admits a unique strong DG enhancement if this set consists of a single element. And that this is the only reason why we sort of change from the standard convention of calling distinguishing between enhancements and uniqueness and strong uniqueness of enhancements is because we want to consider these two different sets of equivalence classes. And in the literature, one would say that a triangulated category T meets a strongly unique DG enhancement if this set has a single element. But we also want to allow for the possibility that, you know, this set contains more than one element. So maybe one could have also alternatively introduced two notions of two equivalence relations, maybe equivalence and strong equivalence. Yeah. So, but there was some way that we needed to have to distinguish between these two equivalence relations and between the two different sets that one obtains. So we choose this way. But I try to clarify this so that there is no confusion that these are the usual things that one is interested, even though the terminology is a little bit different from the usual one. Okay. So what is known about strong DG enhancements? So as far as I know, not that much is known. So here are some results about some categories admitting strong DG enhancements. So already in the work of Lunds and Orlov and the later work of Kanonako and Stellari, later work of Auslander and of Lipertusi and Zhao, they proved, oh, here's a T missing, that so various algebra geometric, let me just say like this to not get into any precise detail, various triangulated categories that arise in algebraic geometry are known to have strongly unique DG enhancements. Also, combining work of Chen and Ye and recent work of Lorenzin, it is known that bounded derived categories of hereditary abelian categories also have unique strong DG enhancements. And as far as I know, there were no other, at least large classes of triangulated categories for which the uniqueness of strong DG enhancements was known. And now there is a natural question. Can there exist an algebraic triangulated category? So admitting at least one DG enhancement that has a unique DG enhancement, but non-unique strong DG enhancements. Yeah? So it's just a very natural question to try to understand how the sets of DG enhancements of two equivalents and strong DG enhancements of two equivalents differ from each other. Yeah? And the answer to this question is yes, and that is what I want to communicate at the end of today's talk. So in order to do that, I also want to explain a slightly more general, well, yeah, a variant of this question that we also address in our paper by introducing the notion of DG enhancement in something that nowadays is called higher homological algebra, that does not have to do something in particular with higher category theory, but is rather about longer sequences of maps than triangles and short exact sequences. So the running joke is that maybe the subject should be called rather longer homological algebra rather than higher homological algebra. Well, you'll see what I mean in the next few slides. So one of the main objects of study in higher homological algebra are the so-called D-set cluster tilting subcategories. So where D is a positive integer. So I'll begin by introducing the notion of a D cluster tilting subcategory. So without Z, here Z is the integer numbers. So this definition is due to Iyama and Yoshino. And this is an equivalent definition. So the proof that this is an equivalent definition is non-trivial, and that's due to Beligianis. So for simplicity, just as the context I want to work in, let's say that T is a home finite Crude-Schmidt triangulated category, and C is a category that is closed on a subcategory of T, that is closed under finite direct sums and direct summands. We will say that C is D cluster tilting if C has no self-extensions in degrees that are strictly between 0 and D. Yeah. So I first want to highlight that if D equals to 1, this condition is empty. And the second condition is that T arises by iterated extensions from C, its first shift, the second shift, up to the D-1 power of its shift. Let me make this statement precise, but also comment that for D equals to 1, we get here 0. So we actually just get that T needs to be equal to C already. So we also get essentially no condition, just, well, the condition that C was equal to T from the outset. Yeah. So the case D equals to 1 just simplifies to C being T itself. So let me unravel precisely without defining this symbol, sometimes called the Verdier product, this second condition for you. So this condition says that for every object little x of T, there exists a sequence of triangles. So each one of these oriented triangles is an exact triangle in the triangulated category T. The objects here don't matter. That's why they are indicated with a dot. Here is the object X. And along the spine of this splicing of triangles, I have objects of the subcategory C, now without any shifts. Yeah. So for example, for D equals to 2, say, 2 cluster tilting subcategory requires that I have no first extensions from C to itself, and that every object in the category T arises as the cone of cone of homomorphism between objects of C. But here, what is interesting is that I can resolve in the triangulated sense in finitely many steps. In fact, exactly these steps, or d-1, depends how you count, an arbitrary object of C by objects of the triangulated the subcategory C without involving any additional shifts. So this is some relatively natural but strong condition on a subcategory, I would say. So that's the definition of a D cluster tilting subcategory, but we are after DZ cluster tilting subcategories and the companion notion of a standard D+2 angulated category. So again, we have our ambient triangulated category T with all the properties I want to have to state results later in this talk. And now I have a subcategory C, which is now DZ cluster tilting. So what does that mean? Well, first, it is D cluster tilting in the sense of the previous slide. So it has no self-extensions in degrees that are strictly between 0 and D, and every object that meets a resolution involving the objects of the subcategory C, plus the condition that C is closed under the default power of the shift. Again, for D equals to 1, if we combine these two conditions, we don't get anything new because one cluster tilting already implied that C was the ambient triangulated category T, which is obviously closed under the suspension. So given this subcategory C, that is DZ cluster tilting, I can now consider the following class of so-called D+2 angles that generalizes the notion of a 1+2 angle, so a triangle. These are diagrams of this form, so obtained by splicing exact triangles in the triangulated category T, such that all along the spine here, I have only objects of the subcategory C. Now, by composing the maps along the bottom part of the diagram with the corresponding shifts, I obtain a map from C1 to the default suspension of this last object CD+2. Now, by the condition that C is DZ cluster tilting, the default suspension of this object is still in the subcategory C. So I obtain a diagram that is contained, if I just look at the outside of this diagram, I obtain a diagram that is contained completely in the subcategory C that looks something like a triangle, but it has now the middle terms. Yeah. So in 2013, Geiskeller and Opperman introduced the notion of a D+2 angulated category by introducing certain natural modifications of the axioms of triangulated categories that I will not mention today, but the definition was introduced in such a way that this theorem would be true. So under these assumptions, have an ambient triangulated category T, a DZ cluster tilting subcategory C, and this class of D+2 angles, I can now consider the triple C, the default suspension of T restricted to C, which is now an autoequivalence of C, plus this class of D+2 angles, and this is now a D+2 angulated category, meaning simply that this collection of D+2 angles relative to this autoequivalence satisfies some suitable axioms that are reminiscent of the axioms of triangulated categories. Now, just to make it very clear, the notion of a one Z cluster tilting subcategory is nothing but just the ambient category T. Yeah, there's something I mentioned now. It's the third time. So it's just to make it clear that in case D equals to 1, we don't get anything new. So we're just discussing just the ambient triangulated category T and not any proper subcategory of it. Okay. Now, the notion of a D cluster tilting, DZ cluster tilting subcategory is related to a more classical algebraic notion, namely that of a twisted D+2 periodic algebra. Now I want to explain what is roughly the relation between these concepts. Suppose I'm giving a triple F, sigma, and pentagon, which is a D+2 angulated category. Typically for us, it will be a so-called standard D+2 angulated category. So coming from a D-set cluster tilting subcategory in some ambient triangulated category. I'll assume for simplicity, well, yeah, these are all technical conditions needed for our results, that it's home finite and Krull-Schmidt, as an additive category. And I will suppose, moreover, that there exists an object little c of F that is basic, meaning when I decompose it into indecomposable objects, all the indecomposable that appear with multiplicity exactly 1, with the property that C generates C as an idempotent complete additive category. Yeah. So in other words, as an additive category, C is controlled completely by the endomorphism algebra lambda of this object C. Now, what's the statement? So it's a theorem that in the case d equals to 1 goes back to work of Freyd and Heller, and in case d greater than or equal to 1 is obtained from work, well, it's proven by Geiskeller and Opperman, and some of the conclusions that I will make depend also on work of Greens, National, and Solberg, and some modifications of these results by Hanihara in 2022. So lambda, the endomorphism algebra of this additive generator of F, is a basic Frobenius algebra. So it's a basic self-injective algebra. It's a finite dimensional algebra by virtue of the assumption that this category is home finite, so has finite dimensional morphism spaces. So this is a basic, basic self-injective algebra. In particular, I can consider its stable module category, which is now a triangulated category. Typical example of a Frobenius exact category. And the statement is that there exists an algebra automorphism sigma, which is induced essentially by this automorphism capital sigma of F, such that the D+2 CCG functor, which is D plus second power of the inverse suspension in this triangulated category, is isomorphic as a triangle functor to the restriction of scalars along sigma. And moreover, if I consider now lambda as a bimodule over itself, so this is the enveloping algebra of lambda, and I compute is D+2 second ZZG, then in the stable module category of bimodules, which is also, so the enveloping algebra of lambda is also Frobenius algebra, then in this stable category, this CCG is isomorphic to the bimodule lambda, but twisted on the right by the automorphism sigma. And an algebra with the three properties above is said to be twisted because of the automorphism sigma, D+2 periodic coming from this automorphism here with respect to the automorphism sigma. So in other words, every time I have such a nice D+2 angulated category, I get a twisted D+2 periodic algebra with respect to an automorphism that it's induced essentially by the suspension automorphism of this D+2 angulated category. And this is in particular true in the case D equals to 1, when I have a triangulated category that is home finite and Krull-Schmidt that is generated by a single object. And these are the categories that Fernando had originally investigated in the case D equals to 1 that I mentioned some slides before. So even in the case D equals to 1, we get access to some twisted three periodic algebras coming from triangulated categories that are additively generated by a single object and with these additional properties. Okay. So with that, I want to so now we've gone from D+2 angulated categories to twisted periodic algebras, and now I want to go back. And for this, I will use some work in the case equal to 1 of Amiot and in general case of Lund. And these are certain D+2 angulated categories that we called Amiot-Lund D+2 angulated categories. So suppose I'm giving, as in the previous slide, a basic Frobenius algebra, and I have an algebra automorphism such that, sorry, yeah, this will come before. Yeah, so I have some algebra automorphism sigma. I will use the symbol p lambda for the category of finitely generated or finite dimensional projective lambda modules, say right lambda modules. And let sigma be the automorphism of this category or autoequivalence given by tensoring with this twisted bimodal, which where now I twist by sigma inverse on the right. If you compare with the previous slide where there was a twist by sigma, this is because before we were comparing with something like an inverse suspension, and now we want the suspension. So that's the reason of the discrepancy. Moreover, I will ask that there exists a class delta in the default in D+2 extension group from lambda to the twisted bimodal, now twisted by sigma. So this is now extensions of bimodules, such that all the middle terms so there is a class in this extension group represented by an exact sequence of bimodules, such that all the middle terms are projective bimodules. Yeah. In particular, the existence of this exact sequence implies that this twisted bimodule is isomorphic to the d+2 CCG of lambda as a bimodule over itself, which was one of the conditions for an algebra being twisted d+2 periodic. So in other words, I have lambda that is twisted d+2 periodic with respect to sigma, and a witness of the twisted d+2 periodicity of lambda with respect to this automorphism. With that, one defines in some way some sequences, some exact sequences in the category of finitely generated projective lambda modules that satisfy certain exactness conditions relative to this class delta. They're a bit technical, so I don't want to explain them. But one defines some nice class of sequences in this category that, as you can see, they look like d+2 angles. And the theorem of Amiot in the case equals to 1, where it's a statement about triangulated categories, and in general case by Lund, where it is a statement about d+2 angulated categories, is that if I consider the triple, the finite dimensional projections over lambda, the automorphism autoequivalent sigma given as above, and this class of sequences in this category, this forms a d+2 angulated category. So really we can go back and forth between d+2 angulated categories in and the twisted periodic algebras. At this level, the relationship maybe is a bit imprecise. Part of our paper is to explain how to turn this relationship into a certain bijection, but I will not explain this today. Just make the comment that up to equivalence, this class of d+2 angles is actually independent on the choice of delta. So I can choose any delta that witnesses the fact that lambda is twisted d+2 periodic with respect to sigma, and I will obtain equivalent d+2 angulated categories. Okay. So in order to formulate our results, we need to now extend the notion of enhancement from triangulated categories to the d+2 angulated setting. So you can view this as a kind of a doc definition, but it's somehow exactly what we need for the results I want to present today. So a DG category A is said to be Carubian pre-d+2 angulated. If again, when I consider the DG Jonetta embedding given by sending an object of the DG category A to the representable DG module represented by A, induces an equivalence between, well, the zeroth cohomology of A and some full subcategory of the compact derived category of A, which is DZ cluster tilting. Yeah, that's the definition. And Carubian again is because, as it turns out, DZ cluster tilting subcategories are closed under direct summons. So this condition is implicitly imposing certain idempotent completeness on C and the zeroth cohomology of A, and therefore the adjective Carubian. However, we will just drop it because we want that this is always satisfied. So the first remark is that if I have a pre-d+2 angulated category, then its zeroth cohomology is a standard D+2 angulated category. Namely, if we apply the Guy-Scaler-Oppermann theorem to the D-set closer tilting category C, we obtain a D+2 angulated structure on C that is canonical in the sense that it is induced by the standard triangulation on the compact derived category of A. And then we transfer it to the zeroth cohomology of A. Yeah, so here we build this notion in such a way that the zeroth cohomology of something pre-D+2 angulated is D+2 angulated. And also the remark that Karoubian pre-1+2 angulated is the same as Karoubian pre-triangulated, because the notion of D-set cluster tilting in the case equals to 1 implies that C should be equal to the ambient compact derived category of A. So we are asking again the same condition as in the Bondal-Kapranov definition. So that will allow me to define the notion of an enhancement of a D+2 angulated category. So what is that? Is a pre-D+2 angulated DG category together with an equivalence of D+2 angulated categories, which again, I only require this equivalence to exist, but is not part of the data. I now lift the equivalence relation on enhancements or extend to the D+2 angulated setting in the obvious way. I have now the equivalence relation generated by existence of quasi-equivalences from A to B, which in particular will induce equivalences of D+2 angulated categories between the corresponding zeroth cohomology categories. And now I introduce the set of equivalence classes of DG enhancements of the D+2 angulated category F, which is now this. So differential graded enhancements, which are now D+2 angulated. So this hopefully now explains the tree in one of the first slides of the talk. And as before, we will say that this triple admits a unique DG enhancement if this set consists of a single element. So now I want to explain some uniqueness result about DG enhancements. So later we will move quickly to the strong DG enhancements in the D+2 angulated setting. So I remind you of the setting. I have a basic Frobenius algebra, an automorphism that makes lambda twisted periodic with respect to this automorphism, the corresponding sigma autoequivalence of the category of projectives, and a choice of an arbitrary Amyolian D+2 angulation of this pair that now I don't decorate with the delta because optoequivalence is independent with the choice of the extension class delta. So the theorem that Fernando proved by himself in the case equals to 1 and together in the general case is the following. Well, first of all, this category does not come from the outset with a DG enhancement, so it's not clear whether it is algebraic or not. But as it turns out, it is it does admit a DG enhancement, and it's moreover unique. So that's the first thing. So this D+2 angulated category admits a unique DG enhancement, and moreover, up to equivalence, there exists a unique algebraic triangulated category in which this D+2 angulated category embeds as a D-set cluster tilting subcategory, and moreover, that triangulated category T that is algebraic admits a unique DG enhancement. So this is to say that this Amyolin D+2 angulated categories are a source of algebraic triangulated categories with unique DG enhancements. Okay. Now, I move on now to the main topic of today's talk, which is the notion of strong DG enhancements. And I'll just briefly explain what do we mean by a strong DG enhancement in the D+2 angulated setting. I just do this briefly because the definition is really the same. So strong DG enhancement A, phi of a D+2 angulated category F is a pre-D+2 angulated DG category. Together now, really part of the data, an equivalence of D+2 angulated categories phi from the zeroth cohomology of A with its standard D+2 angulation that exists by virtue of being pre-D+2 angulated, and to the given D+2 angulated category F. And the equivalence relation is the same as before. I have a quasi-equivalence, so it's generated by the quasi-equivalences of DG categories, which have the additional property that the induced equivalence of D+2 angulated categories at the level of zero cohomology categories commutes up to natural isomorphism with the equivalences phi and psi that are part of the data of these strong DG enhancements. And again, the natural transformation that witnesses this commutativity, it is not part of the data. And I obtain a set of equivalence classes of strong DG enhancements I will denote by SDG D+2 of F, strong DG enhancements that are D+2 angulated of this D+2 angulated category F. And I make again the same definition. We will say that this D+2 angulated category admits as a unique strong DG enhancement if this set contains a single element. Now, before going to the main result of the talk, I want to make a remark that compares pre-triangulated and pre-D+2 angulated enhancements. Actually should have been strong, but didn't fit on the title of the slide. So again, I have my triangulated I have some triangulated category T that it's algebraic, confinite, and Krull-Schmidt. A D-set cluster tilting object, which means simply that the smallest idempotent complete additive subcategory of T containing C is a D-set cluster tilting subcategory. Then I can consider the following. I can consider the strong differential graded enhancements of the ambient triangulated category T. So there is at least one because it's algebraic. And then I can consider the strong differential graded enhancements that are D+2 angulated of the standard D+2 angulated category obtained from this D-set cluster tilting object. Yeah. So we also know that well, yeah, this map witnesses the fact that this exists. Yeah. So this map is just a restriction map. So what does it do? So it takes, oh, sorry, here, yeah, this notation is a little bit misleading. So of course, a strong differential graded enhancement should have been an A and a phi. Here is the phi. And what I do is I just restrict A to the objects that lie in C. And I take the corresponding full DG subcategory of A spanned by those objects and the restriction of this equivalence to that subcategory. Yeah, so sorry for being sloppy. So here I should have really included these equivalences in this notation. Now what's interesting is for D equals to 1, this map is the identity. For D greater than or equal to 2, we don't know whether this map is injective or surjective. Yeah. Yeah, for differential graded enhancements that are not required to be strong, there is no problem. So these two things coincide. But once we ask the compatibility with these equivalences, yeah, the question becomes more subtle. So I don't have time to explain the subtlety, but if you think about it, what do you need to prove? Yeah, so it's not clear, for example, that two equivalences of triangulated categories that agree on this subcategory are already the same, for example, and things like this. So one is to be careful with this kind of, so that would be like injectivity, I guess, of this map. So there are these kind of questions that can appear. And yeah, we don't know how to answer them in general. So this is a small caveat of our results that come in the next slides, or maybe, yeah, small or big, depends your perspective. So now I'm ready. So to finish the talk, I will present our main results on yeah, uniqueness of strong DG enhancements. First, for this, I need a last ingredient. So I need to discuss the stable center of lambda, some basic Frobenius algebra, and a certain map zeta that I'll introduce soon. So suppose I'm giving this basic Frobenius algebra lambda, and I consider a stable module category defined as the ideal quotient of its category of finite dimensional modules, modulo the ideal of maps that factor to a finitely generated projective lambda module. So I want to introduce first what's this stable center. So consider first the endomorphisms of lambda as a bimodule and the ideal of maps that factor through a projective lambda bimodule. The quotient of this is the stable Hom in the category of bimodules, which is nothing but the zeroth Hochschild-Tate, sometimes called Hochschild-Tate cohomology of lambda. Now, the endomorphisms of lambda as a bimodule, these correspond these are in bijection with the elements, I mean, it's an algebra isomorphism with the center of lambda. I lift this ideal to some u lambda and I consider the quotient. So that quotient is what we call the stable center of lambda. So the stable center of lambda is just the stable hom of lambda as a bimodule. Now, as it is well known, the center of lambda is isomorphic to the center of the module category of lambda, which is defined as the endomorphisms of the identity functor of the module category. I have an induced map between these endomorphism algebras or these centers induced by this ideal quotient. Mention quickly on this side that this is nothing but the zeroth cohomology of the stable module category of lambda. Yeah, so notice here the difference. So this is the Hochschild cohomology, but taking in some sense in the stable category of bimodules, and this is the Hochschild cohomology of the stable module category. So tracing this diagram, one obtains a comparison map zeta between the stable center of lambda and the center of the stable module category. That now, once I restrict to the corresponding groups of units, denoted here in the usual way with a cross, induces an induced comparison map, which is what we denoted zeta cross, between the units in the stable center of lambda and the units in the center of the stable module category of lambda. And our main result that will tell us something about existence and uniqueness of strong DG enhancements relies on understanding this map. So this is, I'm almost done with the talk. So this is the first main theorem I want to present out of two. So have a Frobenius algebra, sigma, the automorphism, such that lambda is treated periodic with respect to sigma. I just remind you of all the setting needed to have access to an Amyolian D+2 angulated category associated to this twisted periodic algebra. So the theorem is the following. So first, one can define a certain graded algebra by taking the direct sums of certain twisted bimodules of lambda concentrated in degrees that are multiples of D. And one obtains the following bijections. So here is the map zeta between the units in the stable center and the units in the center of the stable module category. So it turns out that this group of units is in bijection with the set of strong differential graded enhancements of this pair without taking into account the D+2 angulation. So just as a category with suspension. Yeah. So D+2 angulated categories that enhance this as a category with suspension. And one proves this by establishing a further bijection with a certain quotient of the automorphism group of lambda by, it's actually a set of cosets with respect to some stabilizer group of some other action. Yeah, sorry. Sorry, I scrolled too fast. Yes. Now, what is the point is that inside this set, there are those differential graded enhancements that actually enhance the given D+2 angulation that we have chosen. And if one does this all carefully, one can see that under this bijection here, this set we're interested in is identified with the kernel of this homomorphism. Yeah. So the message is the set we're interested to describe is the kernel of a certain homomorphism between the group of units of the stable center of lambda and the units in the center of the stable module category of lambda. So we see that this triple admits a unique strong DG enhancement if and only if the center is trivial. Okay. For d equals to 1, I just do it very quickly. We have the same result, but now it's really a statement about triangulated enhancements. Yeah. So in order to understand the triangulated enhancements induced by associated to this triangulated category determined by a twisted three-periodic algebra, what we need to do is understand the kernel of this induced map between these groups of units. Yeah. And to finish the talk, so I want to give an example where one can understand this map and show that this kernel is not necessarily trivial, so that there exist triangulated categories with a non-unique strong DG enhancement. And remember, these triangulated categories have unique DG enhancements that are not strong. So this answers the question that was towards the middle of the talk. And the example comes from the algebra of dual numbers. Yeah, so take the algebra of dual numbers, k epsilon, where epsilon squares to 0, and the algebra automorphism that it just sends epsilon to its inverse, so it's just the usual antipode. Sigma, the corresponding automorphism of the category of finite dimensional projective lambda modules, and lambda now we just call it an amio triangulation of this pair, because now we are really in the case d equals to 1. So this is really a statement about triangulated categories. So if you're not familiar with d plus 2 angulated categories and you are not sure why you should be interested in them, never mind. This is a statement just about triangulated categories. So as a reminder, here I have the center, the quotient to the stable center, and inside it the group of units. Here I have the induced map from the center of the module category to the center of the stable module category in the inclusion of this corresponding group of units, and I want to describe the kernel of the induced map here. So lambda is commutative, so the center of lambda is just lambda. One can trace all of this, the stable center, and see that under this automorphism, this quotient map corresponds to the quotient of lambda by the ideal generated by 2 epsilon. So the stable module category of lambda is just the category of vector spaces. This is from where it comes the fact that the center of this category is just the ground field K. And here I have the corresponding groups of units, and I have the corresponding comparison map. And now we see the number 2 appear. So of course, the answer to what is the kernel of this comparison map here depends on the characteristic of the field K. We see if the characteristic is not 2, I can divide by 2, and we see that we can identify this with the quotient of lambda by the LDL generated by epsilon. In other words, we can essentially identify zeta here with the identity so that its kernel is trivial in this case. So in characteristic different from 2, we have a unique strong DG enhancement for this triangulated category of amio type. But if the characteristic is 2 is now 0, and then here I just get lambda again. So zeta is just the augmentation map. Yeah, and now we see that the induced map of the on the units sends to the identity all the elements of the form 1 plus lambda epsilon. So we see that we have as many strong differential graded enhancements of this triangulated category as elements of the field K. Yeah, so there are at least 2. So we see that in this case, so for the dual numbers in characteristic 2, we have obtained here a triangulated category with a unique DG enhancement that is nevertheless does not admit a strongly unique DG enhancement. And with that, I would like to conclude my talk. Yeah, thank you for your attention. Yes. So.
Thank you, Gustavo. Let's all unmute ourselves and give the speaker a round of applause now.
Thank you.
If you have any questions for the speaker, you can ask them now.
Gustavo, on that slide that you just showed currently, the kernel of zeta restricted to units has a group structure, right? Does this have any interpretation on these equivalence classes of strong DG enhancements?
I did not think about it. I don't know. Maybe Fernando knows the answer. The way it all arises was really as bijections of certain G sets, let's say. Mm-hmm. So we were really thinking of this as sets. So yes, I don't know.
Well, was just an idea that just occurred to me, not really related to your talk.
Yeah, I don't know if Fernando has something to say about that.
Any other questions? Oh, there's a comment from Fernando in the chat.
Yeah, thanks.
Yes. Yes, so maybe. Well, yeah, I think Fernando already said it. Yeah, there is no need to clarify anything more.
Right.
And another thing, sorry if that's a very silly question, but you said it's higher homological algebra. Is this higher as in higher category theory and infinity categories, or?
No, it's a orthogonal dimension. So it's
Okay.
longer homological algebra. So
Okay.
it's related to here, this length. So the higher is the number here. And if you want, is related to the higher degree of the extensions that appear here.
Okay.
So normally this would be for d equals to 1 will be shorter extensions, and then they become longer. Everywhere everything becomes longer. It's about longer sequences.
Okay. Thanks.
Yeah, so yeah. The last slide where okay. Well.
Thank you, Lucas. Any other questions or comments for Gustavo? Let's see. All the silly questions that I could have asked, I've already asked you in Oslo. So,
Well, they were not silly questions.
like, what was that 3 doing in the subscript? But yeah.
Yes, I was prepared then.
Yeah.
So it was a good question. This time I was prepared.
Okay. Right. So if there are no more questions, yeah, let's thank the speaker again. And before that, let me say the video of this talk. Yeah, well, I'll tell you where the video will go. Okay, let's thank Gustavo again.
And thank you again, Rodrigo, for the invitation.
Yeah, no problem. You were a very natural choice.
Thank you.
Okay, let's stop recording. The slides are available somewhere, I'm guessing.
Yeah, I will put them on my website and I can send you a link.
Yeah, okay.
To your